Okay, we've got an hour before class starts, recording right before class. Hope I can get through this whole thing. Should be quick. All right, so we got a student pushing a book at constant velocity. If you're moving at constant velocity, then your net force is zero. I don't care who's pushing on you. I don't care what all the forces are. They all add up to zero. That's the first law. You got a ball being dropped. If you ignore air resistance, its acceleration, there are a lot of tricky questions that could be asked here. What's its acceleration at the top? What's its acceleration halfway? Doesn't matter. Its acceleration is constant the entire time. Its velocity is going to be changing on the way up. Velocity is positive if you've called up the positive direction. The velocity at the top, if you throw something up, will be zero. On the way back down, velocity would be negative. Acceleration is constant the entire time. It's in magnitude equal to g, and it points toward the center of the Earth. Okay, so this one could confuse people because it's not worded greatly. You may be saying, well, the acceleration is negative the entire time. So it can't be equal to 9.8. That's a positive number. It's just a poorly worded question. What they meant was, what's the magnitude of the acceleration? Because I get to decide whether that's positive or negative. The question hasn't told me anything about whether up or down is positive. I get to make that decision. No matter what, the magnitude of the acceleration is equal to 9.8. And that's what they're asking. Common misconception. No net force does not mean you're sitting still, means you're at constant velocity, meaning two different things. Your speed's not changing, and your direction is not changing. This is false. Does not mean that you cannot be in motion. Really great question here. At the very top, velocity is zero. Acceleration is not zero. Acceleration is down 9.8 the entire time. An inertial reference frame means you have no outside forces, means you're moving at constant velocity. This guy's not constant velocity. Even if you're going at constant speed, your direction is changing. And that means there's an acceleration. Remember, action-reaction pairs always act on different objects. So you got the box sitting on the table, gravity's pulling down on the box, and yeah, the normal force is pushing back up on the box. Those are both things happening to the box. That is not an action-reaction pair. Those do happen to cancel out because the acceleration is zero. The third law pair here, if the box is being pulled by the Earth, the third law pair is the box pulling back on the Earth. The force of the box on the Earth. We've got a rocket in deep space. It fires its engines. So the exhaust gases are pushing forward on the rocket. Third law pair, the rocket is pushing backwards on the exhaust gases. Both of these are true. These are actually both true. I need to look at the answer key that ChatGPT made up here. The exhaust gases are pushed back by the rocket. because they're pushing on the rocket pushes back on them. If they're pushing on their rocket, they exert a force on the rocket. Yeah, this is a goof on ChatGPT's part. Unless it counted both of those as correct. Let me check. Yeah, like it totally goofed. Like here is the solution, and in yeah, in their explanation, they even say the rocket pushes the exhaust gases backwards. That's part of their explanation why the gases push the rocket forward. That's what they had in part A. In choice A, both of those are true. I would find a better question than that. Okay. Make sure I'm recording. Two objects are dropped from the same height. One of them's got some horizontal velocity, one of them doesn't. This is the monkey hunter problem. They both hit the ground at the same time. We already know that is mass. Now you could make the argument that mass is, well, let's see, density is volume divided by mass. So these two are kind of related to that, but that's not what we mean here. By itself, density has nothing to do with inertia. What matters is the total mass. Static friction is greater than the coefficient of kinetic friction. We've gone over this many times. Acceleration while we're in the air, if we ignore air resistance, acceleration is always pointed directly downward. If we're moving at constant speed, I don't like this question. I would not have asked this question. We're making an assumption here. In fact, I would even say false here. The way this question is worded is false. Constant speed doesn't necessarily mean acceleration must be zero, because we could be going around a curve at constant speed. There, we could have centripetal acceleration. Our direction is changing. I hope that's what ChatGPT. Good. Good. Okay. It was a good question. Yeah, I do like that question. You read that and you're thinking linearly. You're thinking when you see constant speed, you're thinking constant velocity, and don't do that. It was a tricky one. A baseball hits, or a baseball bat hits a baseball, then the baseball hits the bat back exactly the same amount. It's a third law pair. If an object is at rest, there's no static friction. I don't even have to read all the choices here. F equals ma. If you have a bigger mass with the same force, you must have a smaller acceleration. That is false. Bigger mass would take more force to accelerate the same amount. These are good questions. I like these elevator questions. So if you're accelerating up, that doesn't necessarily mean you're moving upward. You could be going down and slowing down. Your acceleration would still be upward, or you could be moving up and speeding up. Your acceleration would still be upward. In either case, your net force is up. Remember, the scale doesn't measure your weight, it measures the normal force. Your weight doesn't change. The net force, let's draw this out. We've got weight down, the normal force up. Notice I made the normal force bigger. Because the net force, sum of the forces in the y direction, is mass times AY. I know that that is up. So these two must combine together so that this guy wins. This is what the scale reads, the normal force. That in magnitude must be bigger than the weight. Otherwise, the net acceleration would not be up. So, oh, I didn't mean to circle both of those. Those are really good questions. Static frictional force. There was this other one. Where was that other one? Was this the same question? There was another one with static frictional force. And I want to make sure I didn't accidentally think of that wrong. Because reading this question, I did think of this one wrong. Yeah. Sorry. I read the question wrong. And now that I've read that other version of the question, I realized just static frictional force doesn't have to be zero just because you're sitting still. I just haven't overcome it yet. So if I'm pushing on something, but I haven't made it move yet, that frictional force is pushing back on the object to cancel out my force. Yeah, not always zero. No, I misread the question and thought it was kinetic friction. It's directed in the direction opposite. Oh, circled the wrong one. Opposite to the applied force. That is the correct answer. I'm glad I caught that. Because this is essentially the same question. You're pushing on it. Why isn't it moving? Because the frictional force is equal and opposite to the force. And again, I would have worded this differently. It should be equal and opposite. If it were equal to, then you'd both be pushing in the same direction and the thing would move. What they mean here, again, it's just poor wording. They mean equal and opposite. They mean equal in magnitude, opposite in direction. In order to get an object moving, you got to push harder on it than it pushes back on you. That's impossible. You can never push harder on something than it pushes on you. It will always push back on you exactly the same amount. It's a third law pair. That one, mass is a measure of inertia, not the measure of inertia, a measure of inertia. And weight is the force of gravity. Okay, now we're in sliding. Kinetic friction is less than static friction. You know what's interesting? In more advanced models, we do have what we call dampening forces that are kind of like friction that are dependent on an object's velocity. Air resistance, for example, a skydiver diving through the air, the dampening force, the air resistance force, depends on their velocity. In fact, it depends on their velocity squared. And you could kind of say the air resistance is kind of like friction. But it's not what we mean. When we're talking static friction and kinetic friction, those frictional forces are caused by chemical reactions. The two objects are literally bonding with each other on a chemical level, and we're creating and breaking electrical bonds. That's what's causing those frictional forces. Those are velocity independent. the kinds of friction we're talking about when we're talking about static and kinetic friction. So this one is not true under the circumstances we're considering here. The kinetic frictional force is proportional to the normal force. And if that's a constant force, then the kinetic frictional force will be too. All right, let's do some problems. I copied all these problems down here so I'd have room to work on them. All right, so we got something on the ground, a crate here. That was an ugly looking crate. Being pulled up at an angle of 35 degrees. So we're kind of trying to lift it off the ground. It's not going to come up off the ground because we're not lifting it hard enough to cancel out its weight. But this will be lowering the normal force a little bit and will make it a little easier to slide. You'll see. All right, so we've got weight pushing down. We've got some tension force here. We've got some normal force pointing straight up. All right, so we draw a free body diagram. Weight is down, normal force is up, and I have some tension force here at a 35-degree angle there. I need to break that guy up into components. So let's draw him just separately, just so we can clearly see him. Here's his X component, here's his Y component. That's 35 degrees. So Tx will be magnitude of T, cosine of 35. Just use trig to get that. Ty is magnitude of T sine of 35. Do we know T? No, but we know the final acceleration. So we won't get those yet. Okay, some of the forces in the X direction. We only have one force here. I'm going to redraw this guy here so it's very clear and you can see it. I've got my normal force up, weight down. I've got my Tx here, that guy right there, and then that's a Tx. And then I've got my Ty. It's kind of hard to draw it right there on top of the normal force. I'm just going to kind of put it off to the side. I've got three Ys, two of them up and one down, but only one X. And that's supposed to equal the mass times the acceleration in the X direction, which I know. And I know the mass. So that'd be 20 times 1.5, which I'm pretty sure is just 30. So Tx equals 30. I can now solve for T. I can find the tension. That's all they asked for here. It never asked me to find the normal force, but I could. Oh, wait. I totally lied. I forgot about friction. I totally ignored friction in this problem. I just now looked up and saw that we had friction as well. So we're going to have some kind of kinetic friction here. That will be pushing back this way. We are going to have to find N. Okay, some of the forces in the X direction, then we have two X forces. We've got friction pointing backwards. I've got the X component of tension. And then in the Y, I've got my weight. I've got my normal. And I've got Ty that I'm just kind of drawing off to the side here, because I can't draw it right on top of that. Okay, so in the X direction, I've got adding these as vectors, keeping in mind that this guy's going to end up being a negative number. That will equal the mass times the acceleration in the X direction, and we get the same number here. So 20 times 1.5, 30. Okay, so I can't solve for this guy yet. I'm going to have to find some way to find this guy. Sum of the forces, I'm going to need more space here. In the y direction, we've got the weight. We know what that is. That's mg plus the normal force plus ty. These two are positive, that one's negative. That has to equal 0 because ay equals 0. We know we're not going to accelerate up and down. Okay, so now we've got this system of equations we have to solve. I know that Fk equals mu times magnitude of n, in magnitude here. So I can replace this guy here with an n, and I'll get these two equations. Mu magnitude of n plus tx equals 30. Negative mg plus n plus ty equals 0. And then we have this relationship here. This is actually a more complicated problem than I thought it was at first. All right, let me pause a second. Okay, the best thing to do, I just wanted to think about it for a second, would be replace tx with this, ty with that. Then we have two equations and two unknowns. Our two unknowns are magnitude of t and n. Okay. A lot of times this semester, n is positive. I don't have to keep writing magnitude. You know that I mean, because I didn't draw a vector on it. We know it's already the magnitude, or it points up. We know it's a positive vector in the y direction. I don't have to keep writing the absolute value bars there. Plus, and again, just for magnitude of t, I'm going to write t cosine of 35 degrees equals 30, and negative mg plus n plus t sine of 35 degrees equals 0. Okay, I think we would solve this for n and then plug that in here. So let's see, what do we get? So call that equation 1 and equation 2. Equation 2 then will become n equals mg minus t sine of 35. Plug that into equation 1. So we'll get mu mg minus t sine of 35. I'm going to wait until the very end and type all this in the calculator at once. Plus t cosine of 35 degrees equals 30. Okay, so let's do some distributing here. Okay, I'm going to do a couple of steps at once. I'm going to distribute this mu into here and then move that to the other side. And then I'm going to rearrange these guys. I don't really need those parentheses there. Okay, so I distributed here. Both of these guys got a mu. I took this to the other side, and then I don't like having the minus in front, so I swapped the order. Now I'm going to factor a t out. And I'm divide, so we get this. And I am going to check that. That is a weird looking answer. Let me throw this in the calculator and check and see if it's correct. Oh God, I may have to re-record this. I missed a negative right here. This frictional force points backwards. This is a negative right here. Right here. Because that points backwards. That's the frictional force, mu times n. Which means this is a negative. Which means this turns out to be positive, 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 and positive. Okay, I think that fixes all the signs. And then if we type that in, we get pause. Okay, I think we get 82.1 newtons. That is the tension force. And then we could plug that back in, say here, if we wanted to get the normal force. Okay, I'm trying to rush through these. I forgot about friction at first, and then I got the sign wrong on it. All right, let's do this one. This is a good question. I would put this question on your test. All right, so we're jumping or launching off a 50-meter high cliff. We'll put our x-axis here, put our y-axis here, but we're going up and down. All right, so we're starting at the top. Y0 equals 50. T0 equals 0. X0 equals 0. We're going at a 38-degree angle. So we're going to have to break our velocity vector up into components. So here's our magnitude of our velocity vector. Here's Vx and Vy. These are both initial. We just use trig and we get Vx is magnitude of V cos 38 and Vy magnitude of V sine 38. Okay, over here we'll have T1, X1. We know Y1 equals 0 because this is Y equals 0 here. The water or the ground or whatever. Okay, we've drawn and labeled a picture. We're about to find the initial velocity vector. We're looking for two different things. So now that I've labeled this, I think I'm going to go back and change the labels because I would like to call this T1 right there. So let's call all of these 2. Because I'm going to need an X1, a Y1. I do know that V1 in the Y direction is 0. The velocity in the Y direction, not the whole velocity, up at the top of the crest there is 0. All right, let's find these guys. Oh, 30 meters per second was at my initial speed. So that's V. So 30 cosine 38 and 30 sine 38. I'll pull those on the other screen so I can read them. All right, for the cosine, we get 2364 and 1847. Sure. Both, of course, in meters per second. Okay. Let's find this guy right here first. Remember, we have all of our kinematic equations. You'll have the formula sheet on your test. I am going to use Vy1 equals Vy naught plus AT1. Because I know this, I know this, I know that. I know, let's put this here. A in the y direction is negative 9.8 meters per second squared because I decided up was the positive direction. And of course, I know AX is 0 meters per second squared. All right, so we can solve for T1. So what do we get? We get 0 equals 1847 minus 9.8 T1. That right there. So T1 is 1847 divided by 9.8. That's going to be around 2. .88 seconds. Common mistake people make right now is they think, oh, well, then this is going to be double that. No, that would be double the time to go from the ground through the mountain all the way over here. All right, so that's T1. How far do we travel horizontally? We're going to have to find the time and then find the distance. Like you could get there, you could play around with all the equations, you could try to figure it out. I'm telling you, you're going to have to use y2 equals y0 plus y v naught in the y direction, t2, plus 1/2 a t2 squared. I know this one is 0. I know this one is 50. Got it right there. I know this is 1847. I'm going to have to use quadratic formula here. And then half of g will be negative 4.9 t2 squared. So I'm not going to make you watch me use quadratic formula there. In fact, I'm going to just hope that we got it right over here. Huh. ChatGPT put the initial y at 0 and called down here negative 50. Perfectly fine. Get exactly the same answer. We're going to get exactly the same quadratic formula. There, you can check all that. Check and let me know if it got it right. I'm going to trust it because it seems to be doing a pretty good job. See, I just want to point out here, I've got the 50 here because I called this 0 and this 50. They called this 0 and this negative 50. So they have a negative 50 here and a 0 here. But then if you move that over to this side, you get exactly the same equation. Remember, you can call anywhere you want 0. We're going to get the same equation. All right. And then what did ChatGPT get? 5.6 seconds. T2. And that's reasonable. It should be more than double whatever this time was. Make sure I'm recording. Yeah. All right. Then to get x2, x2 would just be x0, which was 0, plus v naught in the x direction times t2. So that's just that number times that time. So what was that, 38 something? No, 2364 times 5.6. And there, let's just see what they got. 132.4 meters. Don't forget units on everything. Okay, and you could see that, again, ChatGPT did the maximum height a little differently. whatever. Oh, did we even find the maximum height? I guess we didn't find the maximum height. Oh, I didn't answer the question. We found the time of the maximum height, but we never found it. I guess I should finish this up. Y1 then will equal Y0 plus V naught in the y direction times T1 plus 1/2 AT1 squared. So that's going to be 50 plus 18.47 times T1, 188, minus 4.9 times 1.88 squared. So I went through two steps. I used this to find the time, and then this equation to find the height. An alternate way to do it is just use this equation. You never actually find the height. You never find the time. You just find the height. 17. Oh, I guess it's here. 67.4 meters. Plug all that in and check it. All right. So I still got to get through 3 more problems so I can get over to class. All right, we're on an incline. And we're going to try to move the block up the incline. So we're just trying to overcome static friction. So we're not even going to worry about kinetic friction because we just want to just get it moving. And then whatever force we're applying will be more than enough to overcome this and we'll start accelerating. All right, so we got some box, 2.2 kilograms, 2.5 kilograms. We're going to have our weight pushing down. We're going to have a normal force pointing perpendicular to the surface. That's a right angle there. It didn't look like it when I drew it. I'm trying to push up the incline. So here's F, let's call it F applied. Then that static frictional force is going to point back down and it's going to fight me. Until I push hard enough to overcome the maximum, remember Fs is always less than or equal to mu times the magnitude of the normal force. The maximum that can get is when those are equal. And that's the point we're trying to reach. I want to find this to reach that maximum so that these two will exactly cancel out. All right, we rotate our reference frame. Call this your x-axis, the inclined plane. Then your normal force will point straight up. The applied force points right along the x-axis. The frictional force will point down the negative x-axis. And our weight vector will point at an angle of 40 degrees back here. That's weight. Okay, so I like to draw that weight vector over here by himself. Here's my x component. Here's my y component. Here's the magnitude that's mg. Look at the picture. Wx is opposite 40 and it's negative. Both of these are going to be negative. So Wx will be negative magnitude, negative mg. Let's just write it. Negative mg sine of 40 because that's opposite the 40. Sine goes with opposite. Wy will be negative mg. He's negative because he's down. Cosine of 40 because that's the adjacent side of this triangle from this angle. Here's my right angle here. Okay, we can go ahead and calculate both of those, right? Yep. So negative 2.5 times 9.8 sine of 40. Negative 2.5. Notice I had to put in the negative myself. 40 degrees. Don't forget your degree symbol there. All right, let me type both of these into my calculator. 8 sine 40. And cosine 40. So I got 1574. I'm going to write them over here because I've run out of space. 15.74 and 18.70. I guess that's really more 5. Let me round to 2 places more accurately. 15.75 and 18.77. Both of those, of course, in newtons, and they're both negative. Okay, Newton's laws. Sum of the forces in the x direction. What all do I have in the x? Don't forget about this weight vector here. So I've got Wx, that's a negative number. I've got Fs that I want to max out. So that's this guy. And so here, I'll just write him as a vector. And I've got Fa. This guy's a positive, he's a negative, he's a negative. Sum of the forces in the y direction. Let me draw my sigma a little better. There we go. What's in the y direction? I've got Wy, that's a negative number. And I've got the normal vector, that's a positive number. That has to be 0 because a in the y direction is 0. We're not accelerating like this. So that tells me I know what the normal vector is. In magnitude, like remember, that's a negative, move it to the other side, we get normal vector. We know we're supposed to get a positive, we do, and it is 1877. Okay. I needed that for this guy here, this frictional force, because I want to, oh, that's S. I want to find the maximum frictional force. I want to find this applied force to cancel out the maximum frictional force here. And that will be mu times this. So this will be negative 1575, that's Wx, plus mu, what was mu? 0.5 times 1877 plus that applied force. And we want that to equal 0 because we've just now matched it, and any greater force, we would start to accelerate. So we're just about to get the block moving. All right, so like now we just add those together. We're going to end up with a negative number. Move it to the other side, we get a positive. All right, so I've got 1575. Yeah. And that's negative, let me mark that, negative 15.75 plus 0.5 times 1877. That's going to be a negative number. And then when I move it to the other side, I'll get FA as a positive number. And it'll be 6.365. So that's the magnitude. 6.5, I think I said. 365, yeah. Newtons, don't forget your units. All right, let's see what ChatGPT got on that one. A completely different number. 1877. Oh, did I have a sign wrong? Was this supposed to be negative? Oh, I did the same thing again. I left off my negative. Sorry. That's a negative. Both Fs there and Wx are both negatives. I did the same thing again. So in the calculator here, it should have been a negative and a negative, which then would give us positives on the other side, 25.1. So let me clean that up. Because all the other numbers looked right. So I'm assuming they did the problem right. Yeah, 0.5. Yeah, it's the same thing we got. Okay. I don't know if I'm going to finish this by 5. Oh, this one should be easy. Yeah, this one's easy. All right. The thing's in midair. We don't actually we still have gravity. The kids are holding it up. Like this isn't implied or isn't explicitly stated here. Some F from the kids. They have to be holding up its weight or it would be falling down. It would be accelerating down. But we're going to ignore that. We're talking about the left and right forces. Okay, so let's see. We got north, south, east, west. So we've got 12 newtons pulling that way. This kid's pulling 15 newtons back this way. Some of the forces in the x direction will be negative 15 plus 12 will be negative 3 newtons. So by negative, we mean west. A pretty easy one. Okay. All right. Let's see if we can get through this one quickly. This is the hanging picture problem. So we got our kid here, and they're swinging on a rope. These are 25-degree angles here, and they're the same, which makes this the easy version of the problem. We've got T1 here. We've got T2 here. We draw a free body diagram. We're going to have weight down. T1 here. T2 here. We know what's going to happen because these angles are equal. The x components are going to cancel out. The y components are going to add up to the weight. All right, so let's draw a free body diagram for each guy. We could do everything on one picture, but I like to do separate pictures. Here's the magnitude. That's T1x. That's T1y. We got to be careful here. If that's a 25-degree angle, draw a picture here. I don't want to mess up that picture. If this is a 25-degree angle, then this is a 25-degree angle right here. So inside here is 25 degrees. Okay, then using trig, T1y is opposite to 25 and it's a positive. That'll be magnitude of T sine of 25 degrees. T1x will be negative magnitude of T1. These are T1 cosine of 25. Similarly, over here, T2. Magnitude is the hypotenuse. Here's the y component. Here's the x component, 25 degrees again, using geometry. We get T2x will be positive magnitude T2, sine of 20, cosine of 25. I wrote this in the opposite order. Yeah, I don't think I can fit it in here. So I've got x on top here and I've got x on the bottom here. And then the y, sine of 25. Same exact formulas, only both of these are positive. So notice I crisscrossed here. That wasn't on purpose. Okay, Then sum of the forces in the x direction will be T1x plus T2x. Nobody's accelerating here, so that must equal mass times, well, no matter what, that equals mass times the x acceleration, which is 0 because we're not accelerating. All right, so we get negative magnitude T1 cos of 25 degrees plus magnitude T2 right here cos of 25 degrees must equal 0. Don't make this complicated, more complicated than it need to be. The cosines just cancel out. Just divide out that cosine and you get the tension in both ropes is the same. Just move this to the other side. Magnitude T2 equals magnitude T1. So I'm just going to call that T for my next equation. Every time I have a magnitude here in these y's, I'm just going to call it T. Sum of the forces in the y direction will be T1y plus T2y plus the weight vector, which is negative mg. That must also equal 0 because ay is 0. All right, so what do we get here? We get this y plus this y minus mg equals 0. So remember, I'm just calling these t now. I get t sine of 25 degrees plus another t sine of 25 degrees minus mg equals 0. So these are like terms. I can add them together. I've got two of those. That'll equal mg. So T is mg divided by 2 sine of 25 degrees. And let's just trust that ChatGPT got this one right. Oh, whoa. Did I completely misunderstand? Oh, I did. I completely misunderstood 4. Boy, like I've made a lot of mistakes on this one. That's what I get for trying to rush through it. 216.3 newtons. Which is what I think they asked for. Okay, this question, one kid's pulling to the north. Yeah, I totally goofed on this one. All of this was wrong. I don't know how, I swear I read that as one was going east and one was going west. Oh, now I even erased the problem. Okay, now the right way to do this. Like we got class starting in a minute. We've got one force going to the north. We've got one force going to the east. This guy was 15 and this guy was 12. So that east force, if I were to write it out in component form, is 12 comma 0. He's got no y component, only an x component. That north force has no x component, only a y component. Then the net force is just the sum of the forces. Just add the x's, add the y's, will be 12 comma 15. The magnitude of that, just Pythagorean, square root of 12 squared plus 15 squared. The angle, draw out the vector. So here's my net force. The x component is 12. The y component is 15. If I want to find this angle here, I could say tangent of theta is 15 over 12. We're in the first quadrant, so I can just do inverse tangent. And the answers we will get are 51.3 degrees north of east. Won't go back. So here's east and then rotated toward the north. Here's east, here's north. And then the magnitude is, I think I'm going to make it to class on time. 19.2 newtons. Okay, now I think I can export this document. The document's all correct. Couple of issues here in the recording. I'm going to explain this to you in class that, hey, I kind of goofed a couple of times because I was trying to rush. And I think you guys will be okay with that. All right, that's a good place to stop this recording.